Okay, so we'll jump in. Like I said, the syllabus and everything that we talked about on Wednesday, or recorded for Wednesday, is up on Blackboard already. So go look at that video. We'll go through the syllabus and all of these things. The lecture on probability is not that important in terms of a foundation. It's just the background of the way we're thinking about molecules being thrown into energy levels. Okay, just like rolling the dice. Okay, so the main point from that first lecture is the Boltzmann distribution. So this part that begins right here, this Boltzmann distribution function in thermal equilibrium. Okay, so I want to walk through these last 2 or 3 problems, and I want to focus on this idea that the probability is the event you're interested in divided by all possible events. And so for population of energy levels, it's a feature of this exponential energy decay here compared to the energy available in the room. 4449, yeah, PChem 2, thermodynamics, yes. Okay, welcome. Okay, great, welcome. I think of the temperature in the room and the energy available in the room as kind of like a bathtub. So like how much water's in the tub, okay? And that's a nice mental picture in terms of the energy level diagram. If you have an energy level diagram with all these energy levels going up, and I'll just draw it. I'll draw a little bathtub here. So we got a bathtub, and we've got our energy level diagram in here. And the temperature times kT is the level of the water. And the energy of each individual level is right here. So each one of these is like epsilon, 1, 2, 3, the quantum numbers, 4, 5, 6. And so what we're doing, the Boltzmann distribution, is just comparing that energy in the quantum system to how much energy is available in the room. And the population probability is just an exponential of that. So it's less probable that you will populate level 6 than it is level 1. In fact, if you've got this much temperature in the room, this much energy, it's guaranteed that you have population in level 1 and level 2 and level 3 because they're below the water. Okay, it's the population probability drops off exponentially as you go higher in energy, and that's what the Boltzmann distribution is telling us. Now there's some more statistical advantage if you have degenerate levels, and so like let's say level 5 is doubly degenerate, then you have 2 chairs at that level, and you can put more molecules in that level. And so that's this G of I is the degeneracy. So we do a couple of problems in that first lecture. I'm going to go through them real quick, but I'm going to make sure that if you have watched that lecture, if you have any questions, you can ask. If you haven't watched it, go back and watch that. It's a little bit more detailed. Okay, so I'm going to skip ahead to these 2-level problems. Okay, so here's a 2-level problem. What's the population probability of a 2-state system? So we want to know what percentage we have in this level and this level. That's the whole purpose of these probabilities and using the Boltzmann distribution, is to figure out what's the population percentage. And this is something that was controversial early on when they came up with this idea of quantum mechanics. There were a lot of skeptics because chemistry was victorious. I mean, the whole Industrial Revolution was based on chemistry and steam engines. And they knew the way molecules, steam, and water and so on behaved very well. And yet physics failed with the hydrogen atom spectrum. It failed with the photoelectric effect and the blackbody radiation. And so there were some gaps in our knowledge of physics. And it seemed to suggest that nature was quantized. And so they said, yeah, but we're not going to accept that quantum theory until it can determine things like enthalpy and entropy and Gibbs energy and spontaneous reactions and equilibrium constants. And so this first part of the course is the application of quantum thinking to enthalpy and entropy and equilibrium constants and so on. That you can actually get those behaviors, those bulk behaviors, from a quantum view using statistics. And that's what Boltzmann did. He did this in 1870s. Yeah, he started out in the 1870s sort of treating this as a, in his first paper, he was solving for the entropy of gases and their velocities. And he said, let's just pretend that the velocities are discrete, like they're quantized. And he said, but, let's not say that that's what nature really is. It's just a mathematical simplification. But he actually stumbled upon something that was right. And so from the very beginning, some of his math was based upon statistics and just counting the population and energy levels. And that's what led, you may have heard Einstein's quote, you may have seen it on, the internet, quote worthy, and all these little diagrams, a picture of Einstein, and it says, God doesn't play dice with the universe. This is what he was rejecting. So Einstein was against it at first. He was like, I don't believe that nature is based on random statistics, molecules bouncing into and out of energy levels. So let's see if this statistical approach can give us these kinds of answers. Well, it can with Boltzmann's distribution. So let's do this problem. I typically do these problems in table format. Okay, even though there's two levels, it would be very easy to calculate, this, the Boltzmann factor for B0. So for this one here, B0 would equal 1, which is G times E to the minus. And this energy, it has an energy of 0 divided by KT. And so this is just equal to E to the minus 1. And so that's very easy to calculate. Or E to the minus 0, which is 1. So we can calculate that, and then we can calculate the one at 200 and so on, and just do it all sort of without organization. But I like to organize these problems into tables. So let's do it in the table. Also, just for simplification, we've got this Boltzmann constant times the temperature is equal to roughly 200 wave numbers. And that'll help us because this energy up here is also 200 wave numbers. And so when we take this ratio, it'll be E to the minus 1. So we have an index, I, energy level 0, the ground state, and the first excited state. The energy of those levels is 0 and 200 wave numbers. The degeneracy is 1 and 1. And so for the Boltzmann factors, so for the Boltzmann factor for this first one, that's what I just did. That was E to the minus 0, which is equal to 1. And this one was, so B1 is equal to the degeneracy of 1 times E to the minus 200 over 200. So that's equal to E to the minus 1. So that's going to be down here. If you were to type that in your calculator, you'd get 0.38. Okay. Now for the probabilities, we want the particular state that we're interested in divided by the sum of all of them. Well, that sum is called the partition function. So that Q equals 1.38. That's the partition function. That's the sum of both of those factors. Okay. And so now this PI is 1 divided by 1.38, which gives us 0.72 or 72%. And the next one is 28%. So this is 72% of the atoms, ions, molecules, whatever this system is. Maybe it's the ground state is cis and the excited state is trans, So this could be any difference, any quantized difference in any system. And 72% of those are in the lowest energy state and 28% in the highest energy state. And this is one of the, I would say, first sort of assumptions that we make in certain molecules when we're trying to solve the energies. Let's say this is a bond energy. what percentage of the molecules at room temperature are going to dissociate because we're breaking that bond? Well, if this is the energy difference, 28% at room temperature are going to be dissociated. So one of our pastimes in chemistry is trying to figure out how to take a problem and break it into a two-level system, because a two-level system is super easy. Okay. Now let's add a degeneracy. So in this problem, it's the same problem, but now we have a GI of 2. The excited state. So now do you understand more of what GI is? It's just when you have degenerate states, it's the number of degenerate states. Everything else in the problem is the same. So the first one, the ground state, that Boltzmann factor is still 1. Okay, and this Boltzmann factor for the excited state is 2 times 0.38. So 2 times 0.38. Okay, so what has changed? Well, the population of the excited state has changed, and the partition function has changed. So 1 divided by 1.76 is 57%, and 0.76 divided by 1.76 is 43%. So now we have new statistics here, new populations. So this is 57%, and this is what, 41 and a half, or 21 and a half, I mean. Yes.
Is the GI just BI over Q, or is it GI?
It's okay, good question. It's just this BI over Q. And so let me look at, are you looking at an earlier slide?
I'm just looking at the one that was posted, but it has.
Let me scoot back and see. I think you might be looking at this one here.
So there's some errors in the notes. So I noticed
okay,
that
sure. Tell me.
PI has no G involved in 2 of the equations.
Oh, okay.
And PI has the G
not that
involved.
far back.
Not this far back. Okay.
No, I'm on that one. It just has. It has.
Yeah. So this whole piece is what I'm trying to make the notes more consistent, and so I've still let a few of those slip through. So this whole piece would be called BI. Okay, and this whole would be the sum of all the BIs. But that BI is going to include the degeneracy. Okay. So let me scoot forward and find, have you found anywhere those?
Well, it's on this slide. It just has both.
Yeah. So in this slide where we have BI equal to GI,
Mm-hmm.
the stuff. Yeah, the GI doesn't exist in that one. And then in the bottom
But in the table it doesn't have it, is what you're saying. When I'm calculating it for the table.
Well, in
No.
that bottom part,
in the equation it doesn't say it, and then in that bottom equation it also is different.
Oh, okay. Oh, I see. It's what's it's what's posted in the handout that hasn't changed. I'm sorry about that. Okay.
Okay, but
So
it is.
I've corrected these, so you need to correct the handout. So I need to go in and check the handout to make sure it matches better. Okay, I'm sorry about that.
No, it's okay. I just wanted to make.
That's why I did this, because it's foundational, and I want to make sure that y'all have, get these questions answered. Okay.
Okay.
So yes, the BI should contain the G.
Got it.
Yeah. A lot of times it's omitted because it's 1, but that doesn't help you, right?
Okay.
Yeah. So that's. So in this table I've been including it because here it's 0.38, but in the next problem it's 0.76, which means that it's included in that column. So that's why it's 0.76 here. Yeah. Great question. Thank you for, and always if you see mistakes like that, please bring them up right away so that we can make sure that they're clarified. And so 57, 43%. Let's step back and think about how interesting this is. I realize it's just numbers and it doesn't necessarily immediately attract your interest, right? But we haven't changed anything with the temperature. The temperature is still 298. But yet we have more molecules that are excited. That's weird, isn't it? I mean, it's sort of like if there's chairs there, molecules will go there. Okay, so let's look at the equilibrium constant now. Let's put these systems in contact with each other as if they're, I'm going to skip this one for a second. This is treating these two. Let's say that the degenerate one was products and the other one was reactants. Okay, we can look at the partition function ratio, and that is the equilibrium constant. And so if we look at the products partition function, it was 1.76. The reactants partition function was 1.38. And now we have 1.27 as our equilibrium constant. What does that tell us about where the equilibrium lies in this system? So remember that equilibrium constant, you can see it right there. It's products over reactants. And so if that ratio is greater than 1, that's telling us there's more products than reactants. And so we let these two systems come to equilibrium with each other, that just statistically, we're going to have more molecules in the products than we have in the reactants. And so the equilibrium is going to lie more to the right. And we haven't, it's all the same temperature. And so this degeneracy, or the number of energy levels available, is what's driving our chemical reactivity. And we will see this over and over again for the next, several weeks, where we can even get endothermic reactions, things that suck energy, in from the environment to move forward. Normally things go forward if they're exothermic. So endothermic would be uphill, right? And yet we can get those to be spontaneous as long as there's enough energy levels in the product state. It'll be spontaneous going forward, even though it needs energy to proceed. So that's those are our two-level systems. Chemical reactivity, these are some take-homes. Chemical reactivity is driven by the spacing and the availability of energy levels. Okay. Now, we're dealing with just a two-level system, and so let's move to systems that have many more levels. Let's try to get towards molecules, okay? And so molecules can do several things. They can translate, which moves, in space, X, Y, and Z direction. Okay, so we have translational motion in molecules. We have rotational motion in molecules. So if a molecule, if it's not a single atom or a single like ion, if we've got two or more atoms, then we've got a molecule and it will rotate. It has rotational degrees of freedom. And then also, if you've got more than one atom, you have vibrational degrees of freedom. And so each one of those will have their own energy level diagram, their own energy level spacings that are unique to that kind of motion. And we'll look at those next individually. So we're going to do today the translational partition function. And then next time we'll do the rotational partition function and then the vibrational partition function and put it all together. Okay. So let's go to that. It's a translational partition function notes. Let me go over here. Oh. All right. And so we know this, we just covered this again. The denominator in a Boltzmann distribution is called the partition function. We've done some problems with that. Sometimes they use beta, and so I just want to reemphasize that beta is 1 over kT. So you might see beta to the -1, which is kT. K is Boltzmann's constant. It's convenient to use Boltzmann's constant in wave numbers a lot of times because we deal with spectroscopic systems when they're measuring equilibrium, and those are in wave numbers. And so let's look at the probabilities in a two-level system. We just solved for the single probability at a given temperature, but let's look at the temperature. So this is sort of the temperature of the system on the x-axis divided by 298. So this is multiples of room temperature. Okay. And so if we're at if room temperature gives us about 200 wave numbers of energy, 2 times that would be 400 wave numbers of energy. If we're looking at this energy level diagram where we have the energy level spacing is at 400, so this is where our temperature and our energy level spacing match. And this is, we had that one where it was about 27 and 72, or it was 28 and 72. That's what we got in our previous problem. Whenever the temperature matches, or the temperature times Boltzmann's constant matches the energy level spacing, that's the probabilities you have. If we were to cool that down, look what happens to the probability of being in the excited state. The green one is the excited state. So notice the probability of being excited goes down to 0. And the probability of being in the ground state goes up to 1. Okay. So that makes sense. Now, what happens as you heat things up? So if we go multiples of room temperature, so here we're now 10 times room temperature. Can you tell what the probabilities are approaching? And does it make sense? What are these lines approaching in terms of probability? Yeah, 0.5, 50%. And that makes sense if you have 2 options. It's like heads and tails. At that point, if you have high enough temperature, the difference in these energy levels is insignificant. Okay. And so the probability of being in the excited state or the ground state would be equal. And so we would have what we call equipartition. So that's a new term. Equipartition. So the partition function is determining how we partition the molecules in energy levels, and equipartition is as we go to 0.5. And it's 0.5 probability for both. And that's what the equal part, right? Equal. And so we see this word used a lot. And in translational motion, we're almost always in the equipartition range. Well, we are, actually. We have to get it down to incredibly cold temperatures for it to break equipartition. Now let's look at the Q. What are the nature of the partition function in a 2-level system? Notice as the temperature goes to 0, there's only one level that's populated. It's the ground state. That totally makes sense. So the probability of the ground state goes to 1. The partition function also goes to 1. Okay. And so it goes from 1, and then as we raise the temperature, look what Q starts to move towards. It moves towards the number 2. So Q in a 2-level system at 0 is 1. At equipartition, it's 2. Q is kind of counting the number of energy levels populated. So it's giving us a feel for the number of energy levels that are populated. So keep that in mind. In fact, you could write that down. Q is an estimate of the number of energy levels populated at that temperature. And it's temperature dependent. And so these different slides just point out some of the things I've already said. They approach the 50-50 mark at temperatures high, at high temperatures, because the energy level difference is insignificant. And at low temperatures is kind of interesting. We're way below, our thermal bath is way below the excited state here, but yet there's still a non-zero probability of being in the excited state. So it would be a situation where you've got your 2 levels and most of the molecules are down in the ground state and you've got 1 in the excited state. Okay. even though you don't have enough temperature to put all of them up there, you've got enough temperature to excite one molecule to the excited state. So let's talk now about translational motion. So the energies are substituted into the definition of the partition function. So we have this partition function definition. We could put the Boltzmann factor in there. It's missing, but you know, we'll do GI just so that you see that there. And for all of these, GI is 1, so it's missing. So GI equals 1 for all levels. So that's where it went. So what we're doing is we're substituting this particle in a box energy level equation. So the particle in a box, this energy is here, E sub n is equal to n squared h squared over 8ml squared. So that's the energy of a particle in a box. If you wonder where that came from, go back to 44448. Okay, we use that over and over again, the particle in a box energies, and that's the energies for a particle in a box. And instead of I for this problem, we're using n. And so I should probably say G of n. Right? And so now we're summing all of the different quantum states here, and we have a lot of them. Because think about a molecule, all in the early, like first semester, we would put like an electron on a 7 angstrom wire. So the box that electron was constrained to was 7 angstroms. And that was so small that the energy level differences were up in the visible range, you know, 18,000 wave number difference. Okay, now put a electron or an argon atom in a room this size. Okay, that L is enormous. You know, it's meters long instead of angstroms long. And so now the energy level spacing related to the various quantum states is almost nothing, right? Because it's such a big box, the energy level spacing is so close together, the energy levels are almost touching. So we can take this, that would be an enormous sum. It would be summing over something that's like 10 to the 30 energy levels populated. And so let's take this and say that the difference between adjacent ends is insignificant. Now that's a limit as the differences in n become insignificant. That sounds like an integral. So instead of summing discrete energy values, let's integrate over n. Okay, so we can integrate with respect to n, these energy differences. And when we do this, we end up with this equation here. Okay, so the partition function, this is the result of that integral. L has come out. And so we have all of this piece here. It depends upon the mass of the particle, Boltzmann's constant, the temperature, and Planck's constant squared. Okay. Now this useful term pops up, and they call it this capital lambda. And it looks like the de Broglie wavelength in terms of the Planck's constant divided by the momentum, and so that's why this is called the thermal wavelength. And you could kind of think about this as the temperature goes up, this wavelength gets shorter, and you have more and more energy levels populated. Okay. And so this is our partition function. It's the length of the box divided by the thermal wavelength. Now, a box is 3 dimensions, right? So what are we going to do? We're going to have an L in the X direction, Y direction, and Z direction. And so we're going to have 3 thermal wavelengths and 3 L's. Okay. So this just goes to this thermal wavelength cubed. So we went from 1/2 to 3/2. And we went from 1L to L, X, Y, and Z. Or we could just take this and say volume, right? Length times width times height is volume. Okay, so we have volume over the thermal wavelength cubed. That's our translational 3D partition function. funny looking equation. It looks like the V is upside down, right, for the lambda. And so this, we can get rid of volume by using the ideal gas law. And so we don't actually have to know the dimensions of the room. We just need to know the pressure. So nRT over P would give us the sort of the volume term for the gas, but we would be able to then say what the thermal wavelength is or what the volume is in this room, equivalent to that molecule bouncing around in a gas at a given temperature, at a given pressure, know the number of moles, and so on. And so we have this 3D partition function as a function of pressure and temperature, mass of the particle, and the thermal wavelength. So this is all of it sort of crammed together. Notice the temperature's in here twice. Okay, in some equations, maybe in the notes, it has temperature pulled out to the 5/2, but it's best. I've done a lot of work in the spreadsheets trying to do this for different molecules, and I found that it's best to have this sort of gas temperature that's related to the thermal bath in the room. Okay, so we call this the gas temp, and this is for the thermal wavelength. Thermal wavelength. Temperature. I'll show you some plots in a minute where that becomes important. But anyway. Now for grins, and I've got a video doing this on Blackboard, but partition functions are unitless. Okay, and so that's an important thing for you to consider. And this is a whole lot of mess. We've got Planck's constant cubed. We've got temperature to the 3/2 power, really 5/2 power. We have the gas constant, the ideal gas constant, Boltzmann's constant. And so prove to yourself that this mess is unitless. Okay, and then watch that video on Blackboard. A lot of the problems in PChem 2 especially are about the units. And most of the time, if you're just not getting the right answer, it's your units. And so I will strongly enforce that if you're showing me a problem on any exam, that you use your units. Okay. So if you don't show let's say you get the problem totally wrong. You're using the wrong equation. You don't know what you're doing, but you show units, I give you like 30% partial credit. So if the problem's worth 10 points, you're going to get 3 if you would use your units. Okay, because I know if you start using your units, a lot of times you're going to correct your own errors, and then you're probably going to start getting parts of the problem right. So that's just a nice stepping stone. It's like, I don't know what to do, but I'm going to use my units, and if they don't cancel, you're like, oh, maybe I've got the wrong thing here. And then once you start working out those problems, then you might actually get more points. Okay. So there's a couple of practice problems. What's the thermal wavelength and the translational partition function for argon at 1 atmosphere and room temperature? Okay, so we can look up argon on the periodic table. It's 39.95 grams per mole. So we're going to do everything in kilograms. So it's 0.039 kilograms per mole. And we want to get rid of that per mole. So we want to divide by Avogadro's number to get to kilograms. So that's the mass of the argon atom. And so that's going to go in here to this thermal wavelength equation. Okay. And so we have Planck's constant on top. Notice what I've done. Planck's constant is in joules times seconds. So a joule is a kilogram meter squared per second squared. So that squared on the second is canceled with this second in Planck's constant. So that's why it's seconds to the -1 instead of seconds to the -2. It was a joule times a second, so I've already canceled one of those seconds. Okay, I've got the 2 pi times the mass of the particle. So this is my mass of the argon atom. So that's m. This is Boltzmann's constant, K. Now let's look at these units from K. So K is it over here, I'll do it, joules per Kelvin. And so we see that the kilogram meter squared per second squared per Kelvin. So that's the units for the Boltzmann's constant, K, and then we have temperature. So my Kelvin cancels, okay. I've got seconds to the -2 down here, but I'm under square root. So the square root makes that seconds to the -1, so my seconds are going to cancel. So that's nice. I've got meters squared down here, which is going to be meters to the first power after I go through the square root. So it doesn't quite cancel with this meter, but that's okay. This is a thermal wavelength. It should have a distance. And so that's great. So I cancel this exponent and cancel the meter squared down here. Now I've only got 1 kilogram in Boltzmann's constant, but I also have a kilogram from the mass of the particle. So again, both of those, after you take the square root, will be just kilograms, and that's going to cancel with this one up here. So I know, at least with my units, I've got the problem correct. Now I just got to not make a calculator error with 10 to the -23 and 10 to the -34 and 10 to the -26. Okay. One way to do that is to say 10 to the -34. So this is going to be, again, with the square root, it's going to be 10 to the -26 divided by 2. And this is going to be 10 to the -23 divided by 2. So you can hammer the whole thing into your calculator, but you could also do it this way. You could say this is 6.626 divided by 2 by 6.63, 1.38, and 298, all under the square root. Okay. And then you could say times 10 to the -34, and then this would be, I'm just doing the exponents here, so -34 minus 26 over 2, it'd be minus a minus, okay, and minus a -23 over 2. So you could do all of these little things pretty easily by hand and just check your work. So that's one thing I always like to provide you with tools is a way to check your work. So you can hammer it through on your calculator, or you can do it a different way on your calculator and then check your work with your exponents to see if it makes sense. Because when we're dealing with answers that are things like this, 10 to the plus 30, 10 to the -30, how do you know you're right? What makes sense, right? So there's got to be a way that you could think through the problem and say, okay, I'm getting a number that is incredibly small. So this thermal wavelength comes out to be 10 to the -11 meters, okay? But you don't have any experience with thermal wavelengths in your life, right? So how do you know if that makes sense or not? Okay, and so that's why I'm sort of going into detail on other ways to check your work. Now that's the thermal wavelength for the argon atom, 1 atmosphere room temperature. Let's just put it in the box, 24.5 liters. That would be the volume of 1 mole at room temperature in 1 atmosphere. And so let's compare that volume of 0.0245 meters cubed to this thermal wavelength cubed. And this is what we get. So this is Q. And that right there is an estimate of the number of energy levels. Remember what Q tells us, an estimate of the number of energy levels populated at room temperature for an argon atom at 1 atmosphere in room temperature. That's a lot of energy levels. It's not a 2-level system, right? A 2-level system would be ground state, first excited state. Now we're up to 10 to the 30th excited states. That's a lot. So thermal energy, translational energy is thermal energy. For a gas, as we raise the temperature and so on, all of that energy is going into translational motion in the molecule. Yes, it makes sense, I would say. And we can look at this energy spacing. We could just do a sort of a order of magnitude analysis. What I've done here is I've just thrown away all of these pieces. So if this order of magnitude analysis if you throw away all of these pieces here and just look at the exponents, that's what I'm doing right here. I've got Planck's constant, 10 to the minus 34, the mass, 10 to the minus 26, the speed of light here. This again for the energy level equation divided by hc, talking about wave numbers, 10 to the 10, and we end up with 10 to the minus 18. So my point is, this makes sense in terms of the order of magnitude. All right, let's look at this one. These next two problems are the types of problems that I love the most, okay? This one, even though it's fairly complicated, I mean, we have a lot of variables. We have the mass, Boltzmann's constant, temperature, Planck's constant, right? It's overly simplistic because all you got to do is have one equation and one unknown, throw in all your constants. That's rare. Rarely do you have problems that are that easy. Normally you get problems like this. If the translational partition function for an unknown gas is 5 times 10 to the 30 at room temperature, what would it be at 100 C? So we're going from 25 C to 100 C. What would the translational partition function be at 100 C? And you might be saying, well, crud, I've got the equation. I've got it on my note card. I've got it, I can find it in the book, but I don't know the mass, the particle mass. Okay, it doesn't matter. Okay, all you need to know is the proportionality. So a lot of times people will do this. They'll say Q1 over Q2 is equal to T1 over T2. They learn this idea in algebra, high school algebra, and they do this sort of cross product, and they figure out, okay, we can figure out what the second temperature is, or what the second Q is if we know the second temperature. Okay, but notice this is incorrect. Why is this incorrect? It's because of the proportionality. It's to the 5/2. This would work if we put the 5/2 up here. So we can always do the 1s and 2s if we know the proportionality. So here you can do Q2 over Q1 is equal to T2 over T1, but you've got to take this into account. Super important. This is how you do all these problems. You have to know what that proportionality is. It could be the square root, it could be cubed, and this is one of the weirdest ones. This is to the 5/2 power. Okay. So we know what these are. And another thing too is you've got to do Kelvin. And I will break your brain sometimes on the problems by having one of those temperatures be 0 Celsius, right? So what are you going to do if you do it wrong? You're going to put 0 in the denominator or in the numerator, and everything's going to either go to infinity or be 0. And I'm testing you on the test to see if your brain says, wait a minute, that can't be right. And so always convert to Kelvin. I will. And you may say that's a tricky thing. That's actually a blessing because I'm making it blow up on you. If I did 50 to 100, it doubles, and you say it doubles and you don't know you got anything wrong, but it didn't double. Going from 50 Celsius to 100 Celsius is not doubling the temperature. Convert it to Kelvin, it's only a small change. We're going from like 250 to 300. And so we're not really doubling it. We're going from 250 to 300. That's not much of a change. But in Celsius, it looks like we doubled the temperature. So Kelvin is that absolute temperature scale. And so here, it's 8.8 times 10 to the 30. Let me do this last one here, and we're almost out of time. So when would translational quantum effects emerge? So when this system that has 10 to the 30 populated energy levels, if we could lower the temperature to where it had 2, when a Q is equal to 2, then we would see quantum effects, right? It would be like a 2-level system. And so we could just say that we're going Q2 now is 2. Now notice what I did in order to get this 5/2 over to the other side. I multiplied by 2/5. I raised both sides to the 2/5 power. So these exponents canceled each other, and I end up with 2/5 on the other side. So just, okay. And so if I take room temperature and a 5 times 10 to the minus 30 and compare that to a quantum partition function of 2, we end up with 2.1 times 10 to the minus 10 Kelvin. Really cold temperature. It's very difficult to achieve, but that's what's behind these physics experiments called Bose-Einstein condensation. So if you Google that, you'll see some really neat experiments where they're trying to cool gases down to nanokelvin. And they're trying to see quantum effects in translation. Now, what would be a quantum effect of translation? It would be that I'm in a translational box and I can be on the right side of the box or the left side of the box, but never in the middle of the box. So we would see physical matter behaving like waves in space. And so that's why that's a really exciting experiment, and they're getting close, okay? They're starting to see this sort of wave nature of large atoms in really cold temperatures. So atoms like rubidium, I mean, that's an enormous atom. You expect to see hydrogen do some funny stuff, and it does. It tunnels, things like that, quantum effects, but they're cooling down these really large atoms and starting to see some of the quantum effects emerge. So with that, that's pretty exciting. That's the translational partition function. And next time we'll do the rotational motion. We'll see you then.